Now, if light continues to strike a metal plate, will photoelectric effect occur continuously or indefinitely? There is no external voltage source. Okay, so what they are saying is, this is a metal plate and light is falling on this, and this light is of sufficient frequency and it keeps on falling. So if it keeps on falling, they are asking you whether photoelectric effect occurs continuously or indefinitely. That means electrons keeps on ejecting. Is it possible? Assume that there are infinite number of electrons inside. So still this is not possible. It is not possible because as electron ejects, you can explain it in two ways. I'll explain first in the first way, that is, as electron ejects, metal plate becomes positively charged. So metal plate becomes positively charged. That means what? That means it attracts the negatively charged electrons. At one particular point, the attraction is so large that it stops electron from further ejecting. The attraction with electron is so large that it stops further ejection of electron. So that means photoelectric effect cannot occur indefinitely. Okay, the second explanation can be, second explanation is the same as the first one, but they have explained it in terms of potential. See, as electron ejects, metal plate becomes positively charged, right? Metal plate positive charge means potential increases. Now you know that the emitter plate is a cathode, and if the potential of cathode increases, that is actually retarding potential, right? So metal plate's potential increases. That means you will say that retarding potential increases. That is, retarding potential increases. Now, if retarding potential increases, in that case, what will you say? At one point, this potential is so high that it becomes stopping potential. At one point, so many electrons has ejected that this retarding potential becomes stopping potential. And no further electrons can be ejected. And no further electrons can be ejected. In this question, they have asked, a monochromatic light of wavelength lambda is incident on an isolated metallic sphere of radius a. So you have a metallic sphere of radius a. The threshold wavelength of this material of this sphere is lambda naught, and the incident wavelength is lambda, and it is given that the threshold wavelength is greater than lambda. That means the light is of sufficient energy. Now they are asking, find the number of photoelectrons emitted before the emission of photoelectron stops. Okay, so let n electrons are emitted before photoelectric effect stops. So if n electrons are emitted from this metallic sphere, that means the positive charge will develop on this sphere, and that positive charge will be equal to Ne. So the positive charge on the sphere will be equal to number of photoelectrons ejected multiplied by the charge of each electron. Okay, so this is the positive charge that is generated on the sphere. Now due to this, the potential of the sphere is k Ne by R. where r is the radius, or suppose a is the radius, then k ne by a. Now, because the photoelectron ejection has stopped, that means this is the stopping potential. Okay, everybody knows the potential formula of the on the surface of the sphere, right? So this is the stopping potential. Now, Einstein's photoelectric equation, what does it say? Einstein's photoelectric equation says that E is equal to phi plus K max, and K max can be written as EV, right? So from this you will get EV is equal to E minus phi. So from this you will get KNE square divided by A is equal to E. E can be written as hc by lambda, and phi can be written as hc by lambda naught. Okay, so from this you can calculate A.